All right, everyone. This is the finishing of the week 2 notes. I was hoping that my son was going to be better today, but his fever did not go away, and so I'm going to be having to cancel the Tuesday class session this week. And so what I'm doing is recording a few videos series of what the notes we would have covered that day are, and your job is just to watch them before Thursday's class. So we need to finish up the rest of the week 2 notes first because we left off kind of in the middle of the radical equations on the video that I did this past weekend. So this is one that has two radicals in it, and we're trying to solve for x. So when you have two radicals, the best thing is to isolate just one of the radicals first and then get rid of it by squaring both sides, since this is square root. And then what we'll notice is that creates kind of a mess on the other side, and we'll have to isolate the next radical and get rid of it as well. So I'm going to move this minus square root of 5x plus 1 over by adding it. That'll be my first step. So let me rewrite the equation as the square root of 2x plus 11 equals, I'm going to write that square root of 5x plus 1 in front, since that is the part that I moved over by adding, and then we still have that minus 1 that's over there. Okay, so once I've got this, I can now square both sides to get rid of the radical on the left side. So that's just going to be 2x plus 11, because a square and a square root cancel each other out. Now people would love to do that for the right side as well, but there's a problem. This is now a binomial, so you need to write it twice, and we're going to have to FOIL it out because it has that subtraction part. So now I have 2x plus 11 equals square root times a square root would just be the inside, so that would be 5x plus 1 because it's the square root times itself. Then I'll have a minus square root of 5x plus 1, another minus a square root of 5x plus 1, and then negative 1 times negative 1 is positive 1. Okay, so we have 2x plus 11. Now we have, you cannot subtract anything that's in this part with the radical parts, because this is like having a special type of variable. So we have to add just the things that are outside of the radicals together right now. So this will be a 5x, and then a 1 plus a 1 is a 2. And then we have two of these guys. So minus 1 and minus 1 would be minus 2 square root of 5x plus 1. And this is what I meant by you can't subtract these 2's right here, because this second 2 is connected to the square root of 5x plus 1. So our next step is going to be to move everything that's not connected to that radical to the other side. So I'm going to subtract over the 5x, that would make this negative 3x. Subtract over the 2, that'd make this positive 9, equals a negative 2 square root of 5x plus 1. Okay, so at this point, a lot of times people will divide the negative 2 over, but that's going to create some really nasty fractions over here. So even though this isn't completely isolated yet, you can square the radical side if there's a number in front of it. You just have to square the number and the radical. So I'm going to go ahead and square both sides to get rid of this radical on the right. This side again is a binomial, so I'll have to write it twice and FOIL it out. On the right side, negative 2 squared would be a 4, and then the square root of a square root is just the inside, so that'd be 5x plus 1. We need to FOIL and distribute everything, so this is negative 3x times negative 3x is 9x squared. I'll get a negative 27x, another negative 27x, a positive 81. I get 20x on the right side plus 4. Combine the like terms on the left. 20x plus 4. We need to move everything over to the left side, since that needs to be solved like a quadratic. So I have my 9x squared. I'm going to subtract 20, so that makes that negative 74x. And subtract 4 would make that a positive 77. Now, unfortunately, this is sometimes going to happen when you have these bigger problems like this. This is and this is equal to 0 now. This is a non-1, and we can't even pull the 9 out as a GCF because 9 doesn't divide into the other two numbers. So we need to do 9 times 77 so that we can figure out our factors that possibly could make the middle. And that is 693. So I'm going to list some factors of 693. 2 does not go into it. 693 divided by 3 is 231. I don't believe it's divisible by 4, but we can double check. Nope. 693 is not divisible by 5. By 6 would be, nope, doesn't go evenly. 693 divisible by 7 is 99. Getting closer. And 693 divisible by 8 does not go. We know that 9 times 77 works because that's how we got it. 693 would not be divisible by 10 since it doesn't end in a 0, but is it divisible by 11? Yes, 11 and 63. And that's the magical set that's going to add together, if they're both negative, which would multiply to a positive 693, but they will add to a negative 74. So this becomes 9x squared minus 63x minus 11x plus 77 equals 0. Pull out a 9x out of the first pair, that would be x minus 7. Pull out a negative 11, that would also be x minus 7. So I have x minus 7 and 9x minus 11 as my two factors. If I solve those, that would be a positive 7. This one, we would solve it by adding 11 and then dividing by 9. Now, here's the fun thing. After doing all of this work to get rid of both radicals and then having to solve a really not so much fun quadratic equation, which you could have solved that one with quadratic formula if you didn't want to try to factor it. This is what we're down to. We don't know if either one of those solutions works, so we have to check them. So we're going to plug in the 7, so 2 times 7 plus 11 under the square root minus the square root of 5 times 7 plus 1 equals negative 1. That is 14 plus 11, so that's square root of 25. That is 35 plus 1, that'd be 36. Square root of 25 is 5. Square root of 36 is 6. 5 minus 6 is negative 1. So we know that 7 works, so that's good. So let's check the 11/9. And that one's a little harder to check because it is a fraction. We'll have to get some common denominators. And you're welcome to use your calculator to check if you're doing that at home. So that is 22 over 9. Make a common denominator, that'd be 99 over 9. So 22 plus 99 is 121 over 9 for the first fraction and the radical. This is 55 over 9 plus 9 over 9, so that's going to be 64 over 9, which is also perfect squares. That is an 11 over 3 if we take the square root of both of those, and this is 8 over 3. That is 3 over 3, which is positive 1, which does not equal negative 1. So the 11/9 does not work. So after doing all this work, we found out that the solution is the x equals 7. Okay, so that ends the radical equation portion, and now the next little piece in this week 2 notes that we need to do to finish, because we have this plus quadratics in disguise, is rational exponents. So a rational exponent is a power member that is fractional, and it also can be converted into the radical form. We've already talked about this a little bit. So remember, a to the m over n can be written a couple different ways. You could pull the m out, you could pull the 1/n out, because those still multiply to m over n. You can write it as the nth root of a to the m, or you can write it as the nth root of a all to the m power. When solving a rational exponent problem, we have to be careful when even roots are involved, because anytime you're talking about even roots, you have to think about how sometimes a negative and a positive both make a positive when you square them. So we have to be very cautious when solving. So I'm going to just walk through some basic ones. These are all deceptively easy to solve if you just know what to do, but the problem is you have to question whether you should even be solving it. So I'll tell you what I mean as we kind of hit those. The first thing you want to look at when you have an x to a rational power equals a number, so this is the generic setup we're talking about, is that you need to check and see if the power in the bottom is even or odd. This is odd, which means it's okay for this to be equal to a negative number. If for some reason you start off with an even root and it is equal to a negative number, that should not make sense, because an even root should have an answer that is positive, okay? Especially if there's no negative in front of it on this side. So if it's an odd root equal to a negative, you can go ahead and try to solve. To solve, you're going to get rid of the power. So to get rid of this 3/5 power, we raise it to its reciprocal. Now, the next thing we have to be careful about is if you're doing the reciprocal, you're flipping the fraction upside down. So if the number on the bottom in the second part is also odd, there's nothing really to do. You just solve it at this point. But if you flip it and the number on the bottom becomes even, you need to put a plus or minus on the right side because you're indicating we don't really know originally if the base was negative or positive before they applied the even power. So two odd powers on both the numerator and denominator, there's nothing interesting here. You just need to solve it. So what happens is this becomes 15 over 15, which is just x to the first. This is the cubed root of negative 27 raised to the 5th power. So the cubed root of negative 27 is negative 3. If we raise that to the 5th power, that would be negative 243, I believe, but I'm going to double check that. I'm not worried about the negative sign. I know it's negative because it's an odd power, but 3 to the 5th is 243. So negative 243. And this one should work out fine, but you could also plug it back in and check it. Since it's an odd root, the negative under the radical is okay. So let's talk about the second one here. It starts out with an odd root, so I'm going to go ahead and raise this to the 3/4 power. Now, because I raised it to now a even root, because the 4 is in the bottom, I'm supposed to put a plus or minus in front of that. So what I now have is plus or minus the 4th root of negative 49 cubed. Okay, this is a problem. Because we have an even root, we're not supposed to have negatives underneath even roots and still be a real solution. So because this is negative under an even root, we have to say that there is no real solution to this problem. So for part B, even though we started out with an odd root, once we flipped it, it was even, and this negative underneath that root caused problems. Now C is also no solution, but it's for a different reason. This is an even root to begin with. Even roots should not equal negative numbers. Because you're saying that I already took an even root and the answer was negative. So this one is also no solution. It does not make sense. Okay, so let's look at the next one. This is a 2/3, so it's fine. It's an odd root, and even if it is an even root on the bottom at the beginning, you're just supposed to make sure that the number on the other side is positive. The odd root check at the very beginning is just in case there's a negative on the other side, just because you don't want to start out with an even root equal to a negative. So once I flip this, though, this guy is going to become the 3/2 power. And because it's now got an even power on the bottom, we have to make that a plus or minus this root. So this is x equals plus or minus the square root of 25, and then we're going to cube it. So that's x equals plus or minus 5 cubed, and that's plus or minus 125. So there's two solutions to this one. This last one starts out as an even root. It's also equal to a positive, so that's good. But when we flip it now, it's going to be 2/3. So we don't need to add the plus or minus because when you flip it, it's no longer an even root, it's now an odd root. So this would just be the cubed root of 27, and then we're going to square it. So that is 3 squared, which is 9. Now, why did we go through this? Because this is not technically a question on a test. Like, we're not just going to throw a rational exponent solve problem at you. The reason we go through this specific type of problem and walk you through kind of the different cases is because when you're doing the next type, solving equations in quadratic form, which I like to rename as quadratics in disguise, when you're solving those, sometimes your end product will have these rational exponents in it and you're trying to get x by itself. And in the process of solving that, you have to think about, does the solution even make sense? So that leads us to the last topic to finish up the week 2 notes. And then I'm going to have a separate video on what would be covered for the new notes tomorrow for the week 3. This is solving equations in quadratic form. So equations in quadratic forms are equations that have 3 terms, so they're trinomials. The first term has a power other than 2, so it doesn't look like a typical quadratic equation. The middle term has to have an exponent that is 1/2 of that leading term. That's to make it look sort of like a quadratic, because remember, quadratics are x squared and then x to the first. And then the third term has to be a constant. So if you have an equation in this form, we can try to solve them. And here's some examples. So x to the fourth minus 5x squared plus 4 equals 0. Notice the 2 is half of the 4. X to the 6 plus 7x cubed minus 8 equals 0. 3 is half of 6. And even more interesting is the fractional one. So x to the 2/3 plus 4x to the 1/3 plus 2 equals 0. And 1/3 is half of 2/3. So if you have that, that's called an equation that is in quadratic form, or like my favorite term is, I call it a quadratic in disguise. The method we're going to use to solve these is something called U substitution. Now, some of them are easy enough that you could factor it as it is, as long as you're careful with your exponents, and then solve it that way. But because in trig and in calculus, U substitution becomes a really, really important topic and something people need to be comfortable with, we're going to solve it in the notes using the U substitution method. So the first thing you're going to do is identify the exponent on the leading term and determine whether it is double the exponent in the middle. Or you can just say, I'm checking to see if the middle one is half of the first one. Same thing. If it is, you're going to substitute a variable, such usually we use the letter u unless the u is already in the equation, for the variable portion of the middle term. Rewrite the equation so that it takes on the standard form of a quadratic. Solve using one of our usual methods for solving, so factoring, quadratic formula. If you really want to, you could use completing the square. Replace the substitution variable with the original term, and then solve the remaining equation. So we do have to back substitute at the end. So I'm going to start off with an easy one that you could obviously factor if you're comfortable with factoring. You would just use x squared and x squared in your two binomials instead of an x to the first. But I want to show you this one using U substitution. So the 2 is definitely half of the 4, and we let u represent that variable part of the middle, so that x squared. So then I'll rewrite this equation using the substitution that anytime I see an x squared, I write the letter u. Well, x to the fourth is x squared squared, so that means that this would be u squared minus 5u plus 4 equals 0. So now this looks more like a traditional quadratic equation. This would factor into u minus 4 and u minus 1 equals 0. So I get u equals 4 or u equals 1. Now the problem with this is u is not the original variable. And I always joke and say we don't care about u, the letter, not the people. So we have to back substitute and say that x squared is equal to 4 or x squared is equal to 1, because that's what u really stood for. It was a placeholder. So then when we solve this, we're having to take the square root of both sides to get rid of the square. So it's going to be plus or minus the square root of 4 and plus or minus the square root of 1, which means that I have 4 solutions altogether, plus or minus 2, and square root of 1 is also still 1. So we have 4 solutions to this equation. So this is showing you that we can use this idea of U substitution to solve something that looks a little bit more complicated than a regular trinomial. Let's try one that has maybe negative exponents, just to amp it up a little bit. Negative 1 is definitely half of negative 2. So I'm going to let u equal that variable in the middle, x to the negative 1. So then this would be u squared minus 2u minus 35 equals 0. It should always be u squared and u if this is actually half of the original power. So then this would factor into u minus 7 and u plus 5 equal to 0. So u equals 7 or u equals negative 5. Then we have to do our back substitution. X to the negative 1 equals 7. X to the negative 1 equals negative 5. Remember, x to the negative 1 really is a problem with our exponent. It should be rewritten as 1 over x equals 7 and 1 over x equals negative 5. We want to solve for just x, though. So think about this as a proportion, and we can cross multiply. So I get 1 equals 7x, 1 equals negative 5x, divide by 7. And essentially, we're just getting the reciprocals. So x equals 1/7 and negative 1/5. Okay? All right, let's look at one that has a fractional exponent. So we have 1/6 is half of 1/3, because if you think about it, if you do let's see, 2/6 as your leading power here, that reduces down to 1/3. So 1/6 is half of 2/6, so 1/6 is half of 1/3. So we're going to let u equal y to the 1/6. So I'm going to have 2u squared minus 3u plus 1 equals 0. This is a factor by grouping problem. So we have 2 times 1 is 2. Factors of 2 are 1 and 2, so it has to be a -1 and a -2 to make -3. So 2u squared minus 2u minus 1u plus 1 equals 0. Factor out a 2u, that would be u minus 1. Factor out the leading sign, and they also have a 1 in common, so that would still be u minus 1. So I get u minus 1 and 2u minus 1 equals 0. So u equals 1 or u equals 1/2. Add 1 and divide by 2. But remember, we need to back substitute. So y to the 1/6 equals 1, or y to the 1/6 equals 1/2. This is why we talked about the rational exponents a minute ago. If either one of these answers had been a negative number, like a -1/2 or a -1, you would not be able to solve that portion because this is an even root. Even roots have to be set equal to positive numbers. So to solve this, you're raising it to its reciprocal, which is just to the 6th power. So that would just be 1, because 1 to the 6th is still 1. Raise this one to the 6th power, and I have to raise both parts to the 6th. That's going to be a 1 on top and a 64 on the bottom. But again, that's why we talked about the rational exponents a minute ago. If this had been 1 to the y to the 1/6 equals -1/2, we would have said that solution doesn't make sense because a 6th root shouldn't equal a negative number. All right, just a couple more of these, and then that'll be it for the week 2 notes. So we have this one that has not only negative exponents, but they're also rational. -1/3 is definitely half of -2/3 though, so it fits the quadratic in disguise. But notice they're already using the letter u, so I'm going to use the letter v here. V is going to stand for u to the -1/3. So this would be 6v squared minus 13v plus 6 equals 0. I can try to factor by grouping, so that'd be 36, which their factors are 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6. And it looks like if there's a -4 and -9, that will make the -13. So 6v squared minus 4v minus 9v plus 6 equals 0. Factor out a GCF for each pair. This will be 2v is 3v minus 2 minus, I can pull out a 3. That would also leave me with 3v minus 2. So my first factor is 3v minus 2. My second factor is 2v minus 3. So when I solve those, I get 2/3, add 2, divide by 3, and add 3, divide by 2. But remember, we need to set those back into the original. So u to the -1/3 is equal to 2/3, and u to the -1/3 is equal to 3/2. Again, we have a problem with this being a negative exponent, but if you solve the last problem, what ends up happening is if you flip this, you're just going to get the reciprocal of the other side. So we can kind of use what we just learned to say that u to the 1/3 for this guy should be 3/2 because it would flip it after we solve it. And this one will be u to the 1/3 equals 2/3. So we're flipping both sides essentially. So this would be, now I need to take this and raise this side to the 3rd power and do the same thing here. So this one is 27/8, and the other answer is 8/27 because you're cubing both of them. So that is what my u equals. Okay, and then the last one's a little bit tricky because it doesn't look like a traditional ones that we've been doing with the, you don't really see the power right away. This one could be worked a different way. You could solve it like we did other rational equations, but you have to square this stuff first and it just gets a little messy. So I'm going to slightly alter the way it looks by pulling the 2 on top out to the front so that you can see that they have a common fraction in the first part and the second part. So we're going to let u represent that fractional piece. So this only works if they both have the same match as their base. So then this would be u squared minus 2u minus 15 equals 0. So I get u minus 5, u plus 3. So that's a solution of 5 and negative 3 for u. Back substitute, that means x over x minus 2 equals 5, and x over x minus 2 equals negative 3. Think about those as proportions. We're going to cross multiply. So this is x equals 5x minus 10. The other one will be x equals negative 3x plus 6, because it's a negative times a negative. Write that up there. Subtract this over, so that's going to be negative 4x equals negative 10. So I divide by negative 4, that's going to be 5 halves once you reduce it. So 5 halves for the first one. Add this over, that would be 4x equals 6. Divide by 4 and reduce, that would be 3 halves. So we get 5 halves and 3 halves as the two solutions. All right, so that's the end of the first video. I'm going to be starting a second one really soon over the first part of week 3. It might be broken into 2 separate videos just so you guys have less to watch in one sitting. But hopefully by the end of this, we'll be sort of caught up to where we needed to be for Tuesday's class. All right, thanks.